Okay, this lecture will be on esters, particularly their reduction with lithium aluminum hydride and reaction with Grignard reagents. And we're going to get into cyclic esters, which will help cement our understanding. In this first example, we've got just one of the simplest esters imaginable. Just to go over some basics. Reduction with lithium aluminum hydride will destroy that ester functional group. And you end up with just the alcohol. So you reduce this all the way down to the alcohol. With an ester, you'll get a primary alcohol. Incidentally, this group is cleaved off in the first hydride attack. So when hydride adds to this carbon and the carbonyl then reforms, you lose this methoxy group. And so it will hang around as methoxide and it will interact with the aluminum. We don't worry about that. When the water's added, you actually create an alcohol product there as well. In this case, if it's just a methyl ester, you just get methanol as your byproduct. In any reaction we go over, we're always interested in the part of the ester on that side of the carbonyl. However, you would get a mixture of alcohols. In a Grignard reaction here with phenyl magnesium bromide, remember that the abbreviation pH just stands for a benzene ring. You'll see this, especially in this reagent, you'll see it time and time again. In the Grignard reaction, similar to the hydride, the carbonyl oxygen is transformed into an alcohol eventually, but instead of adding hydrogens to this carbon, we've added carbon groups, in this case phenyl rings. Bonded to that carbon. And so in this case we get a tertiary alcohol. Well, now I want to look at a cyclic ester. And notice the reagent here is lithium aluminum deuteride. So we can keep track of exactly where these hydrogens are going, since they're the heavy isotope deuterium. If we think about the mechanism and how this works, it's the same exact thing. In this case, instead of having an equivalent of hydride, we'll have an equivalent of deuteride, which would be D minus. And it doesn't act on its own, it's still bonded to the aluminum. And so it can come in and attack. And we form a tetrahedral. Carbon. Well, these electrons flow back down. We then lose this carbon-oxygen bond and it becomes an alkoxide, but since it's still attached to the rest of the molecule, it doesn't just float away, it's still part of it. And then we have essentially an aldehyde formed on this portion. Well, once you have that aldehyde, a second equivalent of deuteride can come in and attack. Again, we break the pi bond. We've added 2 deuteriums now to that initial ester carbon, Again, being cyclic doesn't affect the mechanism at all. It will affect the product structure. Now in the very last step, where we have water that would be dumped into the mix, that will protonate our oxygens. In this case, notice it's hydrogen, not deuterium. So what you will get on the oxygens would be hydrogens. To make this look a little better, we can number our carbons. We can see we've got a 5-carbon chain where each end has an oxygen. So we have 1, 2, 3, 4, 5 carbons. And so we've made a diol. And then on that first carbon, we have 2 deuteriums. And so this would be your actual product that you would observe. If we look at this molecule, now you should be able to predict what would happen if a grignard attacked. And so predict this product, count your carbons, and see what you get. Perhaps the easiest way to draw it, it might look like this. We've got 1, 2, 3, 4, 5 carbons that were in that initial ring, bonded to what used to be the carbonyl carbon, now are 2 ethyl groups from the Grignard reagent. And the mechanism is very similar to what was shown in the reduction. Alternatively, this is the same structure depending on how you drew it. As this right here. To extend this a little further, thinking about esters, and this will resemble one of your suggested problems that's a mechanism problem. We can look at a Grignard reagent that has basically 2 Grignard active sites in one molecule. So try and see if you can think about what would happen. It's really hard to predict this product without actually working through the mechanism. So I encourage you to go ahead and work through it, or at least do the first step. Basically, this will behave as if it's 2 separate reagents, and it will react one part at a time, not both at once. We can start by drawing a bond using the electrons from the carbon-magnesium bond and attacking our carbonyl carbon. Notice in our structure here we've got 4 carbons in that double Grignard reagent. And so I've added these 4 carbons to our cyclic structure. Then the alkoxide can reform a carbonyl, and the other oxygen can break off to form an equivalently stable alkoxide. So notice in the reaction mixture, we have a grignard, and then we have an alkoxide, but there's no oxygen-hydrogen bond, and so this won't react unfavorably with the grignard. Now that when we've reformed this pi bond, however, the grignard will be attracted to that carbonyl, and the electrons from this carbon-magnesium bond can come in and react. And so we're forming a cycle here. Now we're bonding carbon 4 to the carbonyl carbon. So it's usually easiest to start with that carbonyl carbon, which now is going to be just an alcohol carbon, or initially an alkoxide carbon. And so this was already bonded to carbon 1, carbon 2, carbon 3, and then carbon 4 came around and attacked. And so what we're going to have is a 5-membered ring. And we can verify this by thinking about carbon 1 that was already bonded there, carbon 2, carbon 3, and carbon 4. And now carbon 4 is also bonded to the carbonyl, what used to be the carbonyl carbon. Well, there is also this alkyl chain hanging off here, which is a 1, 2, 3, 4 carbon chain with an alcohol at the end. And that's also bonded to this carbon. You could have it coming off either direction. But we would have this as our product. When you put in the water wash, we'll add hydrogens to those oxygens. We end up with a tertiary alcohol and a primary alcohol on the same molecule. But being able to handle this type of reaction, especially with an ester that can react twice, shows a high level of mechanistic understanding. The last thing I wanted to do was work a multi-step synthesis problem that's just from this chapter and won't really have to do with esters. So like we've done before, the only carbons that you can incorporate into this structure must be derived from cyclopentane. If you look here, we've got 2 cyclopentane rings, so that's convenient. But any reagent you show that will incorporate carbons into the structure, you must show how it was made from cyclopentane. So give this one a try. It'll be important to see that this carbonyl is bonded to a carbon next to where this other carbon group is bonded on this cyclopentanone ring. But give it a try and we'll work through the solution. There's multiple pathways. One's a little bit shorter, but both are beneficial. You're starting with an alkane, really the only thing you can do is halogenate it. So that's a start. Thinking about this over here is a little bit more challenging. We have a ketone product. That ketone could easily have come from an alcohol. In this chapter, especially, with reductions or Grignard reagent additions, most of the products are alcohols, typically secondary or tertiary alcohols. And so if we work backwards from here, a logical molecule that could create this one in one step would just be the alcohol. And we could oxidize this, since it's secondary, with PCC or chromic acid. And so a mixture of these enantiomers would give that. Now notice, I specifically chose to draw a wedge here, and that will help you with the problem in terms of the route. But theoretically, working backwards, this could have also been a dash. That would make it a tougher problem. So notice this trans relationship here. That might clue you in as to what perhaps came before. Anti-addition is always observed with epoxides. Epoxides form alcohols, and epoxides react with Grignard reagents or organocuprates or alkyl lithiums. This would be the structure of our epoxide, then the structure of our Grignard reagent. Could be cyclopentyl magnesium bromide followed by a water wash. Either carbon that this attacked would give us this mixture of enantiomers. This is a meso compound, so there would be no enantiomer there. But we would get a mixture depending which carbon it attacks. Now we have to figure out how to make both of these from our starting cyclopentane. Well, this one's easy. If we just react cyclopentyl bromine, or bromide, or bromocyclopentane, with magnesium in ether, we can make that Grignard reagent, no problem. Epoxides, we know, come in one step from the alkene. And the alkene can be made from the alkyl halide using elimination or E2 chemistry. And so this is a nice sequence, and it incorporates things from this semester and last semester. So it's a pretty good example of what to expect as a multi-step problem. Alternatively, and one thing to work on that'll be good for review, is if you didn't go through an epoxide, you could also have made this molecule going through cyclopentanone. So if you make cyclopentanone from cyclopentane, you could also arrive at this. It just takes a few more steps. But I encourage you to try this pathway if you react with the same Grignard reagent, and then you'll have to move that alcohol around. But being able to do that will be helpful if you get stuck on synthesis problems, having two different routes.